Let's try problem 6.23. The passengers in a roller coaster feel 50% heavier than their true weight as the car goes through a dip with a 30-meter radius of curvature. What is the car's speed at the bottom of the dip? Alright, so let's just go and draw a quick picture over here. Change color. Okay. So here's my circle. And then we have some kind of ride that goes like this, goes through a dip, and then comes out of the circle like that. So right here at this point, this is the bottom of the circle, let's call it. And we know that the radius of curvature is 30 meters. So from here to here is going to be 30. Let's call it R. And we want to know what is the car's speed at the bottom of the dip. Okay, so the first thing to do is just draw a free body diagram. So we have our passenger car, and the forces on the passenger are going to be its weight, whatever the weight of the car is, and then the normal force. But we're told that the passengers in a roller coaster feel 50% heavier than the true weight, which is W. So the normal force is actually what you feel as your weight. So the normal force is going to be 1.5 times W. 1.5 times W, right? Because that'll make them feel 50% heavier. So the normal force is going to be 1.5 W. And then so we know that the net force now, that's all the forces that are going to be acting on them, has to be equal to the normal force, 1.5 W, minus the weight, right? Because it's pointing in the negative direction. And so 1.5 W minus W is just going to be equal to 0.5 W. But then we also know that there has to be some kind of, the centripetal force is going to be what's keeping them moving in the circle. So the net force has to be equal to the centripetal force, which is going to be equal to mv squared over r. Right? This equation right here is just the equation for the centripetal force. So 0.5 W can also be written as, let me rewrite it down here, 0.5 times mass times gravity, right? That's all weight is, just the mass times the gravity. And this is going to be equal to mv squared over r still. And then our masses cancel out. And so we're just left with 0.5 g is equal to v squared over r, but we're trying to solve for the car's speed at the bottom of the dip. So let's rearrange this and solve for v. So multiply r to both sides. 0.5 g times r is going to be equal to v squared. But instead of writing the square, let's just take the square root of it, both sides. So now we just have 0.5 g times r is equal to v. And so now we solve for v, so let's just plug this into our calculator. And this actually comes out to 12 meters per second. And that's our answer. So that's the car's speed at the bottom of the dip. And that's problem 6.23.